We are in chapter 5, yes. Okay. And we will be starting chapter 6 Wednesday. Okay, our quiz questions. Number 1, which thing did Newton discover about gravity?
It's universal.
It is universal. What does it mean to say it's universal?
It's everywhere.
It applies everywhere. Okay. Number 2, in a glass of water, where's the pressure the highest?
Bottom.
At the bottom.
Oh, thank God.
Oh, I guessed on that one.
Remember we have the equation pressure difference is equal to that funny character times G times H. What is that first character?
I have no idea. Delta. I literally have no idea.
A girl wouldn't know, I'm gonna be honest.
That's rho. It's the Greek R. And what does it stand for?
I have no idea. Bro.
Pressure.
It stands for density. So it's the density of the fluid multiplied by G. What is G?
Gravity.
The acceleration of gravity. Well, there's a gravitational force, there's a gravitational constant, there's the acceleration of gravity.
Can we get extra credit if we change your V Walker to weaker?
What?
Farther objects have a V Walker gravitational force. I changed it. Like since can we get
Which problem are we talking about?
First question. First answer.
Farther objects have yes, weaker. There should not be a W there. You're right.
So can we get extra credit?
No, but.
Well, there goes that, guys.
And what was H in that equation?
I have no idea. Height.
Height. H is what height is what H stands for. Or in this case, it would be depth. So this was. Okay, let's stay on this class, please. This is an important equation because it tells us about how pressure varies as we go up or down in something. So we usually talk about water. As you go deeper in water, you're going down and the pressure gets bigger by this equation. But we also have in air. If you go up in air, what happens to the pressure?
I mean, it gets higher, or like the pressure's higher.
If you go up, it gets lower by the same relation. Change in pressure is rho G times the height difference, but the air pressure is the result of the weight of the air above you. So if you go higher, there's less weight of the air above you, hence less pressure. Just like when you go lower in water, the pressure increases because the weight above you is bigger. Okay, third question. The distance between the moon and the earth affects tide because, why does it affect tide?
A, B.
Okay, farther objects have a weaker gravitational and closer objects have a stronger. So this is where we had that actual equation, the force of gravity is equal to this equation. Okay, our textbook uses D, most use an R there. In this equation, what is capital G?
Gravity.
It's the gravitational constant. See why gravity doesn't work? Because lowercase g was the acceleration of gravity, capital G is the gravitational constant. M1 and M2, what are those?
That's a good question.
What does M usually stand for?
The
mass.
The mass. So those are masses of two objects. And then what is D?
Distance.
The distance, the separation between the centers. So if two things are closer, you're dividing by a smaller number. And when you divide by a smaller number, the answer gets bigger. Think of, for instance, 10 divided by 2 is 5. You go to a smaller number in the divisor, 10 divided by 1, it's 10. Right? So if you divide by a smaller number, it gets bigger. So things that are closer have a stronger gravitational pull. So that's why we talked about last class period, who is the force strongest between you and, what other person for gravitational force. And it's the person sitting closest to you because of that 1 over distance squared. Okay, so final question. Which of the following is a requirement for mechanical work to be done? Let's just go one by one. Does it have to have a force?
Yes.
Yes. Does it have to have motion?
Yes.
What direction does that motion have to be?
Parallel.
Parallel. So any direction doesn't work. Has to be parallel, so the answer was E, both A and C. Okay. I'm glad to see you feeling some success. Any questions about the quiz?
I got 100.
That's not a question. That's a statement.
That's the first time I think ever taken
This
this.
is definitely science, not English.
That is a statement as well.
Jesus Christ.
Okay, so we are going to continue talking about fluids. And I forgot to bring I thought my demonstration was already in here, so I'll have to go grab it midway through the lecture. Actually, go ahead and connect to Woo Clap right now while I go and grab my demonstration.
Well done. It said somebody left their. Oh, this is so.
Well, they should get it then.
Got my demo. Okay, I'm going to assume that everybody is pretty much in there now and move on. We don't have a first question for a little bit. Remember, we talked about buoyancy. And buoyancy, we talked about it was the very last thing that we talked about. I talked about Archimedes and him sitting in the bathtub, jumping out with a eureka moment. Remember that?
Yeah.
Okay, good. So, don't want to be up here talking to myself. It's not very useful to talk to yourself. So buoyancy is related to that. Buoyancy is the result of the net force of water pressure on an object. So here is I'm going to call that a potato just because it looks like a potato to me. And that potato has water on top, water on the sides, water on the bottom. First thing that we've already learned, the force due to pressure always presses in. So everywhere on that potato, the force due to the water pressure is going into the potato. So you see on the left side and the right side, it has those arrows pointing in toward the center of the potato because that's the direction the water pressure is pushing. On top, it's pressing into the surface, which is roughly down. The surface isn't perfectly horizontal, so it moves around. Bottom, it's roughly up. But the pressure is not the same everywhere. Where's the pressure greater on this potato?
The inside, bottom.
The bottom, just like we had in the quiz question, right? The pressure is greater when you're deeper. So the bottom part of the potato has the deeper elevation or position, deeper, so greater pressure. But a second thing, I said the force due to pressure is always pressing in, but the value for that force is pressure multiplied by the surface area. So if the pressure is bigger, the force per unit area is the pressure. So the force is going to be bigger on the bottom. Now remember, pressure is force per area. So I had the suction cup out last class period, and we demonstrated with that suction cup how the force of air pressure is strong enough to hold that piece of metal up. But it depends on how big the area is. If it's a small area, it's going to be a smaller force. A bigger area, it's bigger. Well, the potato has as much surface on the top as it has on the bottom. But the pressure on bottom is bigger. So if you have the same area on top and bottom, but the pressure on bottom is bigger, which force is bigger? The force pushing up from the bottom or the force pushing down from the top?
Up from the bottom.
Up from the bottom. So that difference in the force, the net force, is the buoyancy. So buoyancy is the net force caused by the pressure being greater at the bottom. And Archimedes, with his eureka moment, he realized that there's a relationship between the water that is displaced and the upward force, the buoyant force that is acting on the object. And whoops, I should have stayed here. This here is our real key. The buoyant force, the net upward force caused by the water pressure on an object, is equal to the weight of the water it displaces. Now, if you think about displaces, when Archimedes got in that tub, he saw the water level come up. He displaced or moved away that volume of water. And it would have lowered his weight. If he had stepped on a scale while he was in that water, he would have weighed less. I think I talked about in class the effect of floating or sinking, didn't I? And if you float and you step on a scale, you would weigh nothing, because the scale is measuring how much force is necessary to keep you from dropping. If you float, there's no force necessary to keep you from dropping. So we are going to explore this in lab on Thursday. We're going to study the buoyant force in lab. So Archimedes' principle that the weight of the displaced fluid is equal to the buoyant force was discovered by Archimedes and relates to buoyancy. There's the actual statement there. And we can apply it to gases and liquids. So a gas, what do you know? Well, let's just think about this. If I have a candle burning, we often talk about heat. And we say the heat does what? What is the action of the heat?
Heat rises.
We say heat rises. Now, if we're going to study this like a physicist, we notice something interesting, right? I should say a physicist. I should say a scientist, because all scientists can go through the same process. We know something interesting, that the hot air rises. And so then what's the next step in the scientific process?
After the hot air rises,
After the observation that the hot air rises.
we would test it.
Have to do something to test. Have to have something to test.
I have no idea.
Okay, remember for the test, you have to have this, you have to know this, you got to memorize. First thing is observe something interesting.
Oh, the scientific.
Yeah.
Oh, yeah.
What's the second step?
Create a theory.
Create a hypothesis.
Yeah.
Close.
And what are the three things it has to do?
It has to,
Be scientifically proven.
Based on scientific ideas,
based on scientific ideas,
has to
be able to be tested.
make predictions that can be tested. What's the third thing? The third one's the obvious one.
It has to be proven by the test.
So it has to be like a question.
It has to explain why the thing you observed happened. So our hypothesis needs to explain why the hot air is going up. And so now we have a little bit here that would help us, because with buoyancy, the force buoyancy is equal to the weight of the displaced fluid. And if something goes up, what can you tell me about the net force if I suddenly start accelerating upward?
Oh, it's really strong.
Not really strong. How fast I accelerate would be related to the strength. But if I accelerate upward, I have a net force that is upward. Because Newton's second law says the acceleration is the net force divided by mass.
Saying that for
So-
be weight greater than your mass.
Well, no, my net force would have to be upward if I started accelerating upward. So like when I jump off the ground, the normal force was bigger than the force of gravity while it was jumping to make me accelerate upward. So here we have air that is starting at rest and then it starts moving up, so it has an upward acceleration, which means we have to have a net force up, which means that it must have one possible hypothesis, the correct one. It has a buoyant force that's bigger than its weight. Well, its weight, what's the equation for the weight of an object?
Oh God. This is gonna be on the test, right?
Sure.
No, I meant like it's gonna be on the list of formulas.
The
Yes,
weight equals
yes.
force net equals mass times acceleration of gravity.
Well, yeah, the force of gravity is m times g. That's the weight. So the weight is mass times gravity, but we just learned that mass change color for writing this. We learned that mass is equal to density times volume. So this could be written as the density of this would be now hot air times gravity times the volume of the hot air. So that's the force of gravity. But from the preceding page, from Archimedes' principle, we know that the force buoyant is equal to the weight of the displaced air. So the displaced air would be the mass displaced air, density of cold air, times G times the volume of the hot air. Why volume of the hot air? Because that's the volume that was displaced of the cold air. And so our hypothesis says that the net force must be upward. So that buoyant force, what direction is the buoyant force? The net force on you when you're floating in water due to the water alone? Up. So that force buoyant is up. What direction, of course, is the force of gravity? And so we know that if we add those together,
It'll equal 0.
not equal 0. And I will, as soon as I finish writing this, go back to why. It's greater than 0 because it's accelerating upward. Right? The hot air, it went from rest to moving up. So it had to have an upward net force. And so those are the two forces acting on it. They have to be upward, so greater than 0. So just moving this across the equation, I have an equation that says density of cold air times G times the volume of the hot air must be greater than density of the hot air times G times volume of the hot air. Now there's some redundancy here, right? What can I do to simplify my equation? I can cancel. And so I end up with the density of the cold air must be greater than the density of the hot air for that hot air to rise. And that plays into further topics in today's lecture. That is, in fact, the case. But that would be a hypothesis that we could draw from the observation that we say heat rises. Notice I've been saying every time hot air rises, because that's what's really happening. Hot air rises. Because it's less dense. And less dense things will float on more dense things. So if you float in water, what does that say about your density? The density of your body.
It's lighter than
Okay, the density is lower than the density of water if you float.
what's the path flow?
If you're neutrally buoyant,
You know, if you put like this.
well, that's still floating. If you stay at the surface, that's floating. If you sink to the bottom, well, that's sinking. Neutrally buoyant is you could be in the middle of the water and you just stay there, you wouldn't go up and down. And if you're neutrally buoyant, if your net force is 0, then we would have the case that I think somebody said that the sum of those forces is 0 if you're not accelerating. And then that would imply that you have the same density as water if that was you instead of hot air. So staying on this topic, how do you suppose a hot air balloon flies?
It makes itself lighter.
Heat.
Like heat helps it rise, and your right hand is less.
Well, if you heat the air becomes less dense. And so that hot air balloon is filled with air at a high temperature, thus less dense air than the air around it. And so you have this force, the buoyant force. Of course, the volume of cold air displaced is equal to the volume of hot air inside your balloon. And your net force is what I have written there for the balloon part. And if that net upward force equals the weight then of what you're hanging from the balloon, you have a canopy with people in it and hot air or gas and a burner. If the net buoyant force, this calculation here, is equal to the weight that you're hanging from it, then it'll just stay at one elevation. But of course, what's going to happen to the temperature of the air in that balloon over time if you do nothing?
Well, it's gonna cool down and then you're gonna see it.
It's going to cool and you're going to start to descend because your upward force decreases. And so you turn on the burner, you make it hotter, you can reach neutral or you can go higher if you make it even hotter. The experiment we are going to do in lab is going to be essentially what you see here. We are going to measure the buoyant force two ways. The first way is, actually I'll go through the measurements here instead of saying the first way. First, we measure how much our object weighs, force of gravity, in air. So air means that it's in air. Then we're going to put it into water and measure the force of gravity in water. The two are different. And we're like, what? The force of gravity can't change. mg didn't change. But it turns out we're not really measuring the force of gravity, even though we say we're weighing it. We're measuring how much upward force is necessary to keep it from falling. And when you put that object in the water, what's different compared to having it in the air?
Well, Mark's here, into it.
The density of air is much less than the density of water, like what's 800 times less dense or something. So there was a small buoyant force in air that we just completely ignore. But when we put it in water, we can't ignore that. Think about it. Let's suppose that you are neutrally buoyant, that you essentially have the same density as water. If you're in air, you have a buoyant force that's 1/800th of that. So if you weigh 150 pounds, your buoyant force, take 150 divided by 800, it's less than what, a quarter pound? So we ignore that. But in water, we can't ignore it because the water is, as Jessica said, much more dense. And so when you put it in the water, it has a buoyant force. In this case, the buoyant force is equal to the difference in the two. And so it would be, notice it says 3 kilograms, it'd be 3 kilograms times G minus 1 kilogram times G. You can't say force and have units of kilograms. That's just wrong. So that's my buoyant force. And then separately, we weigh how much water was displaced. And in this case, we had 2 kilograms of water that was displaced. So the weight of that is 2 kilograms times G. And according to Archimedes, those should be equal. So in lab, we're going to do that. We're going to weigh the object in air, weigh the object in water, take the difference of those, and that is the definition of the buoyant force. And then we're going to measure how much water is displaced and calculate its weight and compare them because according to Archimedes, they should be the same. So that's what we're doing in the lab this week. Okay, our first woo clap question. I've got. Okay, so on which of these blocks submerged in water has the buoyant force? Wow, that's not even English. Which block will have the greatest buoyant force on it? These were copied from the textbook. They're actually given to me, and I just put them in where I see them as useful.
Okay, world clap. Let's do this.
You have 3 answers already. There's 4.
Why is not letting me?
Not letting you, huh? Okay, restart so you can get it in there, Jessica.
Does that mean that we all put ours in?
I only have 4 right now because. Okay, there we go. There we got the 5th one. So what we had was one person that said this. We had 0 people say this. We had one person that said this and 3 people that said that.
I'm sorry, I'm laughing because we're all just on different levels at this point.
Yeah. And it'll please you immensely to know that, well, what's the principle here?
None of us were right.
That's correct.
Darn.
So we were asked about buoyant force. What does Archimedes say? Well, it's important to do these. These are checking to see understanding, and now I know I need to go through this more. What does Archimedes say about buoyant force? The buoyant force is equal to
The weight
of
of the water.
the weight of the displaced fluid. So in this case, the weight of the water that was moved away by the object. Now, in all 3 of these cases, the object is submerged. So that means that the volume displaced is equal to the volume of the object. So what we need to do is rank these by which one has the biggest volume to the smallest volume, and then we can answer the question. So if we look at these in terms of volume, they all have the same mass, right? Kilograms a unit of mass. What's the relationship between density and mass? What is density?
What's the difference between density and mass?
No, what is density?
Density is mass.
It's not equal to mass. It's related to mass.
Volume.
And volumes related to mass and volume.
Pressure.
No, that's pressure. Or yeah, the definition of density is how much mass you have in a volume. So density is mass divided by volume. What did the buoyant force depend on?
How much mass you have in volume?
It depends on the amount of water displaced.
Yes. Density of the fluid, well, this is water in every case, so that's the same for all of them, times acceleration of gravity, g, that's the same for all of them, times the volume of the water displaced. So we need to solve that density equation for volume. So if I take this equation right here, and I want to solve it for volume, what are the math steps to solve rho is m over v for v? What do I have to do?
Wait, what are we trying to calculate again?
We're trying to take this equation up here in the top
The mass times
and
the
solve it for volume.
mass times the density of the water.
Not quite. That's why I asked what are the math steps, so we make sure we know how to get there. I have density is mass divided by volume. I want volume by itself. What would your first step be to try to get volume by itself? What was that?
Put numbers in there.
Multiplied by mass.
We don't have numbers. Not multiplied by mass. We have volume in the denominator, in the divisor. And we want volume on top because we're trying to solve for volume. So the first thing that you would want to do is to multiply everything by volume so that you have volume in a numerator on top of the division sign instead of denominator. So now these volumes cancel. I have volume times density is equal to mass. But I want volume by itself, so how do I get the density away from the volume? If volume times density is mass, how do I get volume by itself? I have to divide by the density. So I have the volume is equal to the mass divided by the density. Whoops, I put delta instead of rho. That was a lowercase delta what I wrote. So volume is equal to mass divided by density. So I'm looking for the thing with the highest volume because you're going to have the highest buoyant force if you have the highest delta V, the highest volume displaced. So, what row would give me the biggest volume? Would it be the largest density or the smallest density? The smallest. Because you divide by a small number, you get a big answer. So the answer is the smallest density is the largest volume. So I could rewrite that this here, because it's low density, that translates into high volume, which means high buoyant force. And so the buoyant force is greatest on the aluminum. Now, the one that got the most answers all the same. Let's confront why people said that, because it's pretty logical. I understand how people said that. Why do you suppose, if you're not one of those three, or if you are one of those three, why did you choose that they're all the same?
Well, because it says 150.
Because they all have the same mass.
I purely guess.
Guessing would also get you wrong answers reasonably often. So they all have the same mass is true, but the question didn't ask us about its weight. It asked us about the buoyant force, so we have to analyze what's the buoyant force dependent on, not just what's the force of gravity dependent on. So this one here was thinking about gravity instead of thinking about the buoyant force. So low density things will have a higher buoyant force because they're displacing more water. Now I have a lot of things dealing with this, like how do you make an iron ship float? Iron is more dense than water. If iron is more dense than water, what should it do if you put it in water?
Sink.
Sink, because more dense things sink. Less dense things float. So iron's like, 3-4 times more dense than water, something in that ballpark. So it should sink readily. And you probably noticed that. If I take this and drop it in the swimming pool, why yes, it sinks because it's iron. So how do you make a boat float?
Put air in it.
Put air in it. You put air in it, and air is, I said, 1/800th or so the density of water. Air has a very low density compared to water. So air obviously floats. And so to make a ship, you hollow it out, and it displaces a volume of water that equals the weight of the ship, but you have the edges sticking up, so it could displace even more. And so you probably have noticed that you can tell the difference in a laden ship and an unladen ship by how high it floats in the water. Laden means it's loaded with stuff. You can, on ships, they will have markings on the prow and maybe on the sides telling you how much water it's displacing, so you can see how loaded it is. So you're just displacing water so that the weight of the water displaced is equal to the weight of the ship, and it floats. Now shifting to gas. I said that when you heat air, what happens to its density?
It's less.
It's less. When you heat air, the density drops. So why? We have to understand what a gas is before we can go very far with this. So a gas is a bunch of molecules that are flying. Molecules are little bundles of atoms, which we will discuss carefully when we get to the chemistry section here. But they're molecules that are flying around and not attached to each other. So let's talk about other phases. Solid is a phase. Liquid is a phase. Gas is a phase. Those are the three common phases. You also have other phases like a colloidal suspension or a plasma. There are other phases, but these are the three common ones. What makes a solid different from a liquid from a gas? Have you ever even contemplated what makes them different? Why water melts or ice melts to become water?
Because
Okay, heat
And it changes form.
changes form.
The density,
It's what?
the density.
The density does change. Water is odd compared to most things in that density regard, by the way. But in a solid, your atoms have a fixed position. So each atom or molecule is in a fixed location and doesn't move. Now they can have really tiny vibrations, but they don't move from that position. They just do little vibrations about that position. That's a solid. So fixed positions there. ED, fixed positions. In the liquid, you have a surface here. Within the liquid, the molecules are free to move, but they can't leave the liquid. And in a gas, they're completely free of each other. That's the difference in a liquid, a solid, and a gas. In a liquid, the molecules are moving all about. You wouldn't think that. You put your hand in water, you don't feel anything hitting it. But they are. They're moving all around in there. But when they get to the surface, they get pulled back in and they're not allowed to leave. In a solid, believe it or not, the molecules in the table are moving, but they're vibrating really small amounts. So you might as well think of them as stationary. And in the air, they're moving all around. So molecules are constantly hitting your body. And how do we interpret the molecules hitting your body? Do you feel the molecules hitting your body?
You shouldn't.
You actually do. The air pressure you feel is the molecules hitting your body. And we talked about, having your hand out the window of the car and feeling the air and stuff. You're feeling the molecules hitting your body. So you do feel them, not one by one, but as a combined effect. So the pressure is the combined effect of all those molecules bouncing off of your body when they hit it. So that's what pressure is caused by in air or in water. It's the molecules bouncing off of you. Now notice here this statement. Temperature is a measurement of the kinetic energy per molecule of the gas. Temperature. What does temperature mean to you?
The presence or absence of heat.
Presence or absence of heat. To me, until taking physics, temperature meant very much the same. There's more heat, less heat. It turns out my understanding of heat and my understanding of temperature were a little not right. So temperature is actually a measurement telling us about the kinetic energy of the molecules. If you have a high temperature, the molecules have a high kinetic energy. What does it mean for them to have a high kinetic energy?
Lots of movement.
Lots of movement. So hot air, the molecules are moving a lot faster. They're hitting your body harder, and thus there's more force when they hit your body and higher pressure. So temperature is a measurement telling us about how fast the molecules are moving, and technically it's telling us about the average kinetic energy of the molecules. Pressure is about the molecules hitting the surface and bouncing off of it. Now we have gas laws. If you cut the volume in half, you're going to double the density, and the molecules, they're going to be closer together. They're going to hit a surface more often. You're going to increase the pressure. Now I'm going to very quickly go through Boyle's law. Boyle said if I keep the temperature constant, if I change the pressure, the volume changes, so pressure times volume is constant. Now, I'm going over it quickly because the end result is the one we care about. So we have Boyle's law. This question doesn't. We also have Gay-Lussac's law, and we have, something in my mind goes blank. Charles' law. Yes.
I'm going to be honest. I
Yeah.
understood jack squat enough to write a question. That means I didn't understand anything at all from the lesson.
That's troubling to me.
I took down notes
Notes.
except for the last one because you jumped through it really fast. But I can't come up with a question.
Obviously, I can't write your question for you.
I understand that.
I would like to talk to you about it afterward because, what is the point to come to class? We're in class, and that has to do with the teaching. But we, look through your notes and try to come up with something there.
I'll do my best, but it's not going to be 15. Or less likely to be.
So we have Boyle's law that says you keep the temperature constant, pressure times volume is constant. We have Charles' law, Gay-Lussac's law, Avogadro's law. When you put them all together, you get one equation. For an ideal gas, which is the only kind we're going to talk about, the pressure times the volume is equal to N, which is telling us how many molecules are present, multiplied by a constant and the temperature. So there is a fixed relationship between pressure, volume, temperature, and the number of molecules, which is new to us. And we will have to pick up here next class period. Have a good day.